So thank you very much indeed for the introduction, Elliot. And thank you very much for the introduction, Michelle, because a lot of what you've said leads very nicely into the presentation I'm about to make. I think one of the strengths of ICSTI and one of the things that makes it very interesting to come to this forum is the involvement through its association with the scientific unions of working scientists. And I'm delighted that there are working scientists with us today, and they're showing us their work and the excitement it generates in the field, and consequently the importance of getting that work correct. Henry Rzepa is a working scientist that many of you in the audience also will have heard of. He's a chemist at Imperial College London who's been involved in interactive visualization of chemical structures more or less since the dawn of the internet. And he made an interesting contribution to a mailing list on molecular visualization software a couple of weeks ago. He opined that publishers are likely to love interactive PDF because it's easy to archive. But such objects are data impoverished in the sense that Horst referred to. You're interacting with a representation of the data, an engineering-style 3D object primitive assembly. With certain other software, and he referred to Jmol, which is a program I'll tell you a little bit more about very soon, one is obliged to provide semantically accurate data, such as chemical markup language or some other chemical format that has information about the chemical primitives, if you will, rather than the geometric primitives. A PDF object, he says, is simply a rendering of that data. His point is that from a Jmol visualization, you should in some way be able to retrieve the molecule to do other things with it. By all means, he says, provide both, and certainly interactive PDFs are a novel technology that are very important and exciting and are going to be of immense use in fields where there are no other avenues to such visualization. But Henry would urge that a 3D object, a 3D PDF, should not be the only object provided. And that's a point of view with which we're sympathetic. In the International Union of Crystallography, for some time, we wanted to have interactive visualizations of crystal structures. And it seemed to us that this software, Jmol, was a good candidate for this. It's been around for a little while. Here is an example of an article in Biochemistry Journal of a couple of years ago showing a protein structure binding to a nucleic acid. And fingers crossed, if this all goes well, we can go to the Biochemical Journal website and we can look at this object. And you'll see that it's a visualization of a protein nucleic acid complex as a 3D manipulable object. We can pull it around, look at it from different angles. And when we looked at these figures, we thought that the journal had presented them very nicely. So there are various options here for stripping away the different conformers of the protein. You see as I clear each checkbox. So you get a simpler and simpler view. And this represents the author's view, or the author's set of views. We had this discussed earlier. It's additional semantic content. These are views that the author considers important in visualizing certain aspects, the way the different conformers overlap here. But what's nice about Jmol as a tool is that here you are actually dynamically visualizing aspects of the underlying chemical structure. And Jmol comes delivered as a Java applet embedded in the browser, and it has its own set of controls. So a reader could bring up a menu and go in to look for a different style of rendering and could say, well, this cartoon representation, it's a formal representation which conveys a lot of information. But in this particular case, I would gain more by looking at a space-filling representation of the protein molecule. So in this way, the reader is interacting through Jmol with the data in a very dynamic sense, can select different visualizations to suit that reader's requirements. So as I say, we found this a very attractive presentation, and we wanted to follow suit. But it seemed to us that in this example and others that we looked, there was a great deal of overhead involved on the part of the author and indeed of the part of the publisher in putting this together. Each different example we looked at seemed to be a bespoke solution with different sets of controls that must have required a great deal of thought and effort to put together this complex sort of multi-valued presentation. That is expensive. It's expensive in monetary terms because you've got to pay a consultant to do it. It's expensive in time terms because the author has to consult with the consultant and explain what they want and so forth. Because it's not a standard part of the journal workflow, it's expensive for the publisher to add this to the particular article on an individual basis. And what we were very keen to do was to bring this type of technology into our journals, but to make it easier for all concerned. We first of all delayed getting into this because we wanted to make sure we had the right tool for the job. For a number of years, Jmol has been around and it's been able to show protein and small molecule structures. In doing so, it's really derived from two other programs, Rasmol and Chime. But Jamwal, by being able to show both styles, was embarking already upon a process of assimilation of different fields of chemistry and structural sciences. And since the time that we first began to look at it, it has grown to be able to show extended crystal lattices, so molecules or other atomic structures packed in regular array in a crystal lattice. It has changed, or it has added visualizations of the types of structures that are interesting in inorganic crystals. So you can show coordination polyhedra or voids and channels in zeolite structures. And from our perspective, the thing that really clinched it, that said now is the time to use this tool, was when Jmol became able to show displacement ellipsoids. In a crystallographic experiment, the result shows not only the position in three-dimensional space of each atom in the structure, but also how mobile it is within the crystal structure, how much each atom can move around its mean position. And these ellipsoids, barely visible, these ellipsoids are visual representations of the amplitude of the oscillations in the three spatial dimensions. So a crystal structure solution is actually a six-dimensional object. And since then, since we decided that that made Jmol a candidate for our own involvement, it acquires additional features. It can now show diagrammatic representations of the symmetry elements within the crystal lattice. It can show electron orbitals in molecular species. And very recently, it can actually superpose electron density meshes over the candidate structure. So now that we had the right tool for the job, we wanted to make it easier for, in the first instance, for the author to use. Jmol is a professional level program. It has very powerful capabilities for visualization. But there's a steep learning curve to learn the scripting commands that are required to get the most out of it. So our approach was to develop a toolkit that we could make available to authors to make it much easier for them to use this tool. And here's an example of the toolkit that we make available as a web application from our own website. And you can go along to that and select the type of structure that you're wanting to visualize. Depending on which choice you make, you get a slightly different set of tools within the palette that's brought up. And you will upload a data file, which is a small file showing the three-dimensional positions and the amplitudes of oscillation of the crystal structure. You upload that file to our server, and the server then reserves storage on our servers, on our publishing server, And it downloads to the browser the Jmol application within this applet and a number of palettes of tools that you can use to modify the appearance of the structure. So I will do something quite simple here. I will just change it to a different orientation. I will perhaps change the default atom sizes. So this is an ionic solid, and it might be appropriate to scale the atoms to the ionic radii rather than just some standard proportion of the default bonding radii. And I will save that. Okay, so I have now created a chosen visualization. This is my first pass at the interactive figure. In clicking save, I then transmit back to the server all the scripting commands that have been pulled together through that visual interface. And the server does a number of things. One thing that it does is that it runs the Jmol application again in a background mode in order to create a high-resolution two-dimensional image. So the first thing that we do is we generate a TIFF image at high resolution showing exactly this view because it's generated by exactly the same application. That is going to be used as the static figure in the PDF version of the picture. That currently is the fallback archival format because the TIFF, rather than the PDF itself, but TIFF is regarded as a stable graphical format. Jmol, it's cutting-edge technology. Perhaps it won't last as long, but we hope it will, and we believe it has features which make it a good candidate for an archival strength application. Okay, but what you also see in this window is the preview of the figure that has been created. So this is fully manipulable. It's a three-dimensional object. And this is the interactive figure that will be published in the journal if the paper is accepted and no further intervention takes place. It's so closely integrated into the workflow that that is figure one of the paper that we're in the process of writing. Okay? As a standard, as a free gift, we provide a little widget which toggles the spin, because with these 3D visualizations, that's always the first thing people want to do. Okay. And we provide facilities for the prospective author to go back and do some more things. Okay, so this is an inorganic structure. So we might be interested in the extended packing. So I'll draw a 3 by 3 by 3 unit cell arrangement in space. I'll realign it a little bit so that it looks prettier. Zoom it out so that it fills the frame. And I'll superpose upon that the coordination polyhedra. So these are geometric conventions that in the field are used to highlight the ordered arrangement of the differently related atoms in the structure. Now, clicking on the top is Jmol's default rendering of the coordination polyhedra, which is often good enough, but in this particular case isn't quite refined enough to show the type of coordination that the author would want to do. So we have an alternative which allows more manual control over the representation. So here, this is the same view that you've just seen, but now we can control the distance within which the polyhedra geometry is calculated, and we get a much better rendering, which will be much nicer for the reader to see the geometric relationships. So that wasn't difficult to do. I knew how to do it because I've done this before. If you're a complete novice and don't know how to do it, every time you see a little green icon and you click on it, you get context-sensitive help, which explains in as much detail as we think is necessary what the effect of that control is. And sometimes these are very detailed notes that pop up. And you can move that around if that's in the way. You can collapse it, and it's there when you need it, and it's not in the way when you don't. I could choose to save that instead of the original view, but what I will do in this case is I will open up another window in the toolkit where I can grab the current visualization, the one I've just set up, which, as it were, behind the scenes is a set of scripting commands. And I can pull all of those scripting commands into this window, which will save it and bind it to an HTML button in the form that I'm about to build. Okay, I can put a caption on it. I can say this is the coordination of the structure. And if I go back to this preview screen, what you will see now is that little button has appeared called continuation. Coordination. I haven't typed that very well. So this is a caption annotating the dynamic button that I've just set up. I've done all of this without needing to know anything about Jmol, the Jmol scripting language. However, the toolkit facilitates the use of Jmol scripting if you do happen to know a little bit about the subject. So for instance, I happen to know that within the Jmol language, the command stereo on will give you a side-by-side stereo pair, and stereo off will undo that. And I'll put a little caption alongside that. The typing's not very good this morning. Stereo. And you'll see dynamically as I do these things and go back to the preview screen, I now have a little button which allows me to toggle on the stereo view on and off. Save everything I've done, and again it's doing a round trip to the server at the publication office, and when it comes back you will see once again the original view, because that's what we selected as the characteristic view within this figure. That's where that will be the static representation in the PDF. But we have these other controls, these other buttons that we've set up. Because we used specific scripting controls, we can actually apply the stereo visualization either to this view or to the other one. And we can flip between them. So we have provided this toolkit to make it easy for the author to add in all these dynamic controls, to put in the types of different views, the different preferred views that so attracted us in that biochemical journal article. And we haven't lost the feature that allows the reader still to go in and say, well, that's all very nice, but in this case, the coordination polyhedra are getting in the way. I prefer to see it just as a ball and stick representation. So this is maximal flexibility in accessing the data. Okay, and we provided support to the author by these context-sensitive pop-ups, but also by writing manuals, providing online examples and tutorials. Just very quickly, this is an example of a protein structure done in the same way, and how it looks in its different manifestations. In the PDF, you have a very nice representation derived from Jmol. But if you go online to the full-text HTML, you see the figures, our traditional way of presenting them, they appear as a thumbnail, but when you click on the thumbnail, you pull up the dynamic picture, again with controls that allow you to toggle the spin on and off. And this is integrated within the journal workflow. That's, of course, very important from the publisher's viewpoint. You want to make it cost-effective in production environment. Now, in publishing a paper, an essential part of that workflow is the peer review cycle, and that's already excited a significant amount of interest this morning. With this architecture in place, we can take this tool which I've shown you, so you can go to our website and just use that tool in isolation in order to prepare a figure in advance of publication. But we also have integrated the tool within our submission system. And I'll now go to our submission system, and this is all live, by the way. This isn't demo. This is a live paper as it was being reviewed. Now, this is one that has been published, so I'm not breaching confidentiality here. But I've turned the clock back a little bit just to take you to the website prior to acceptance, while it was under review. And at this stage, the author has uploaded the CIF data file, which is a mandatory component of all our structural articles. We require deposit of the structural data. Another structural, another data set, the HKL files, which are actually the processed experimental data upon which the model is derived. And you'll see by this stage the author has already uploaded a number of conventional figures. At this point, if you then scroll down to this form, there is an option to create an enhanced figure. And for this paper, that would be figure number 5. This is a small molecule structure, as opposed to the organic one that we looked at. And we just leave checked this directive which says use the data file that has already been uploaded as the primary data underpinning the publication. But if, for instance, you want an enhanced figure of a related data set, you could also upload it at this point. The button says generate enhanced figure, so we'll click on that and see what happens. And you see exactly the same toolkit. The default representation of an organic compound is different. We show the single molecule by default rather than the lattice, but of course the author's free to choose that if need be. We'll just go to a control that allows me in one click to select an atom and center the view on that atom. Zoom out a little bit. And there are also simple ways of moving the labels. I will do this, I think, just for one because it requires 2 hands. So you can drag the labels around very easily in order to get an artistic, a non-overlapping layout. And that seemed trivial, but actually if you have to do that sort of manipulation using the Jmol scripting language itself, you'll realize how much authors will appreciate that facility. So you can go on, as I showed before, to build up ever more elaborate visualizations. Here I just have a simple representation. I save it and come back to the same sequence before, where I could go back into the editor and make further changes. Or I can now go back to the submission page to see what I have done. And here, appended at the bottom of all the figures that have been uploaded, there's now this dynamic figure. And the dynamic figure still has links which allow us to edit again and to view it in its interactive manifestation. The reason the edit control is there is that this is a figure that is subject to peer review. The reviewer might ask for changes to the figure. The view that the reviewer sees is very similar to that, but of course it's a shorter page. It doesn't have the features that allow an author to upload more stuff or to remove material that has been uploaded. But for the interactive figure that we've created, there is a button allowing the reviewer to pull down the interactive figure. So this is all still at a privileged stage. Not only the reviewer can see the figure, but can interact with it, can see what it is that the author is trying to tell. But the reviewer still has access to the data and can get in and do things. Now I'm a little bit sad that time is running short, because what I also wanted to show you, perhaps, have I got 5 minutes? 2.5, I'll speak very quickly. One of the points I want to make is that the tool Jmol is specific to chemistry, but the architecture for managing all this within the publishing and review workflow is something that I think could be adopted in other environments and by other journals and so forth. The architecture allowed us to build on that's all right, so my demonstration isn't going to work, so I won't show that. But I will tell you what I was going to demonstrate, and then over coffee I can show interested people. It allowed us to provide an authoring tool that operates in the same server-client relationship, but does something really quite interesting. In the case of protein structures, the workflow in science is somewhat different. The typical author will begin by depositing the structure in the protein data bank and write the article subsequently. The tool that we have generated, it operates in a similar sort of way. It has a similar look and feel. You go to it, you type in the PDB code of the structure that you deposited, and the application goes to the protein data bank, downloads that particular structure into your authoring environment, into your workspace, and then allows you to extract data from the PDB file. Some data will be there, such as the author's names, the names of the compound, and so on, and import those into the publication. You can build up the publication with more tools, editing tools that we provide. You can also put in the visualization of the figures, if that's what you want to do. And it is a little sad that the technology's let me down, that this demo isn't live, because one of the other things that we do is that we provide links to databases, so that in downloading the PDB file, you find a list of authors. You can click on a search button next to the name of one of those authors. That will dynamically search the World Directory of Crystallographers, our own database of prospective authors, give you a list of potential hits, and if you locate a hit in a little pop-up window, a single click will transfer all of the affiliation and other data that is held for that author straight into the authoring form. You carry on, you complete authoring the paper through that form, building the figures and the visualizations as you want. At the end of the day, you click on Save, and you get a completely coherent article saved in a variety of formats, RTF and PDF, if that's what you want to show to your colleagues. What is actually saved is an enhanced annotated version of the data file that you originally downloaded from the PDB. A little bit like magic, but the point is that the PDB format is fully compatible with the structural format that we developed within crystallography that treats data and what was traditionally metadata on an equal footing, and can hold in a single vehicle all the science, all the article, all the data, and now, in the work that we've done most recently, the scripts that generate author-driven visualizations. So I better stop there before I get punched. Thank you very much.
We have time for maybe a question or two. Brian? Yes, sir.
Horst Kramers again. Brian, I had the opportunity in the beginning to read a few pages from the fourth paradigm, and I just want to pose a question to you. How far are you offending to Gray's law number 3? Because it's a Gray law says, page 5, bring computations to the data rather than data to the computations. You know, I just, you see, if a book of Microsoft on page 5 brings laws, you see, they don't say if it's local laws, municipal laws, or state laws, international, eternal laws, or whatsoever. So I just want to ask, as far as I understood, you have to upload your data. You have these scripts are run on the server rather than on the client, and so on.
The scripts are actually run in the client, but the scripts are stored on the server so that they can be repurposed. They can be published to the client application. Okay. So we're trying very much to have an environment where the data and the computation are served simultaneously or in parallel. We're working towards that. It's a server client-based architecture, and the relevance of the server, in our view, the primary relevance of the server is in providing the long-term storage, the archival backup for the data which is most conveniently visualized in the client application.
So Brian, in your last, maybe it's inherent in this last part, but what I was thinking as you were going along was that it's very nice to have this interactive view of the molecule, and embed it in the paper effectively, but it still separates essentially the annotation from that molecule, which is the rest of the paper, from the molecule itself. And what we'd like is a greater level of interaction between, essentially, let's just make it simple, the text and the figure. So for example, when you moused over a little piece of the molecule, the relevant text that the author had annotated effectively about that molecule would be highlighted, or so there would be a greater correspondence between the two. Is that something you foresee in the future?
Well, I'm told by my managing editor, who's here, that that's something we did on Thursday night, but because I was already here, I haven't had a chance to look at it. No, yes, seriously, that's something we're clearly working towards, and we're beginning to approach it. We've got a number of applications where you can begin to do that. You can annotate certain parts of the text and link directly to the visualization, and you can go the other way as well. Jmol and the essentially the Jmol API, and the fact that you can communicate through JavaScript calls to the application. Can I just say, this is a personal benefit I've felt in working on this project. I had the opportunity to meet the lead developer of Jmol in person in doing research to support this project. We had a very productive lunch together down in Oxford. And I said that Jmol has lots of very powerful features, but it would be nice if we could extract information from the CIF file that Jmol has ingested that Jmol does not directly use, but feed back into any application that's communicating to Jmol. And he said, that would be useful, would it? He said, and I said, yes, it would be useful. He said, well, we've got 5 minutes while the lunch is being served. I'll do it for you. And unfortunately, he entered a bug into the programming, so he wasn't able to do it by the end of lunch. But as I had breakfast the following morning, I got an email saying I stayed up late and the job's done. So Jmol now can fully parse a CIF file, retain data that's not relevant to the visualization, but feed that data upon request in the form of data structures to any cooperating application. I subsequently had tea that day in Oxford with Alyssa Goodman, who works with Michelle, and we talked a little bit about interactive PDFs, and Alyssa and Bob Hansen were at the same meeting. By the end of the week, Jmol was able to export U3D format. So Jmol is an open source application that can provide the raw material to go into interactive PDFs as well. So these technologies aren't in competition, they're synergistic, and one's going to be perhaps more appropriate than others. But I would like, I mean, from our perspective, we would like to see more effort put into the applications that visualize the data in this very real sense, and perhaps aren't so reliant upon geometric primitives as in the current state of interactive PDF.